Welcome to our first lesson on Nuclear Chemistry 1. In this lesson, we will get to know who discovered radioactivity. We will find out what is radioactivity, the types of radioactivity we have, and then we'll also compare the differences and, if possible, similarities between nuclear reactions and chemical reactions. On your screen, I'll be using a red laser as a pointer from time to time, so if you can see the laser moving on your screen, I'll be using it as a guide in this lesson. Let's begin. The discovery of radioactivity is attributed to a man known as Henry Becquerel. His discovery is commonly described as an accidental discovery. He was working on a series of experiments on phosphorescent materials when he decided to keep uranium salts in a photographic plate covered in black paper. By the next day, Henry Becquerel realized that the parts of the photographic plate containing the uranium salt had darkened or become black. And this made him wonder what was happening. He proposed that it might be that the uranium salt emitted some radioactive particles that caused the area of the plate to darken. So on your screen you can find a picture picked from the internet showing how the photographic plates which contain the uranium salt looked like, and the dark area is what Henry Becquerel proposed as the area which absorbed the radiations which were produced by the uranium salt. Two scientists continued the work of Henry Becquerel. They are Marie Curie and Pierre Curie, husband and wife, of course. They worked on spontaneous radioactivity and continued the work of Henry Becquerel. So these three scientists are the ones that are credited with the discovery of radioactivity. What is radioactivity or radioactive decay? It is a process in which an unstable atomic nucleus changes into a different nucleus with the emission of radiations which carry energy. So the key words in our definition are unstable atomic nucleus, which will change into a different nucleus with the emission of radiation and energy. The radiations are the ones which carry the energy. So radioactivity is just an atomic nucleus which is unstable trying to become stable by emitting radiation. Let's look at an example of a radioactive decay process, or a typical example of radioactivity. Example, the decay of carbon-14. Carbon-14 can break down or can undergo the decay process to form nitrogen-14 with the emission of a beta particle. So carbon-14 decays to nitrogen-14 and a beta particle. So radioactivity results in the formation of a new nucleus, which is different from the original. If you compare carbon and nitrogen, they are different elements altogether. carbon, even though they have the same mass number 14, the atomic numbers are no longer the same. So we have formed a different element which is different from carbon, and that is nitrogen. Radioactivity also results in the emission of radiations which carry energy. Example of such radiations is what you have on your screen. We'll talk about the types of radiations later. But this radiation here is a beta particle which has been emitted. And the type of radiation which is emitted depends on the radioactive decay process. Since radioactivity converts one chemical element to another element, they are also sometimes referred to as nuclear transmutation reactions, or you can simply say transmutation reactions. A transmutation can occur in two ways, or can be achieved in two ways. You can force it, or it can occur spontaneously. You can bombard a nuclide with a particle, and that transmutation is known as artificial transmutation reaction or artificial radioactivity. Sometimes these transmutation reactions occur naturally, can be found in nature, and we call them natural radioactivity or natural transmutation reactions. So spontaneous disintegration of a nuclide is what we are talking about as a natural transmutation reaction. Let's define natural or spontaneous radioactivity. It is a type of radioactivity that occurs naturally. It means you don't force it. You don't have to use any particle for the nuclide to decay or to break down. An example is what you have on your screen as a natural transmutation reaction. We said transmutation reaction is when we convert one chemical element to a different chemical element. So in the reaction, you can see that nitrogen 16 has been converted to oxygen 16. And this is a transmutation reaction because we didn't force it. We didn't bombard nitrogen with any particle. So this is a natural transmutation reaction or natural radioactivity or spontaneous radioactivity. They are the same. The particle, the radioactive particle that is emitted here is a beta particle. This is also another way you can represent a beta particle. Let's look at the second type of radioactivity, known as artificial radioactivity. Artificial radioactivity or artificial transmutation reaction. It is a type of radioactivity that is produced by bombarding an element with high velocity particles. The high velocity particles could be a neutron or alpha particle. These special reactions take place in a special machine or device known as a nuclear reactor. We'll look at components of a nuclear reactor later under nuclear chemistry. Let's look at an example of an artificial transmutation reaction or artificial radioactivity. On your screen, you have aluminium-27 with atomic number 13. Now we are coming to bombard aluminium-27 with helium atoms or alpha particles. And this is what the screen described as a bullet, because we are going to fire or bombard the aluminium element with these alpha particles. So this one is not occurring on its own. It doesn't occur naturally. We are forcing it. Because you are forcing it, it's no longer natural. We describe it as artificial or man-made. That is why this nuclear reaction is known as artificial radioactivity or artificial transmutation reaction. So we have bombarded aluminum-27 with helium atoms or alpha particles to form phosphorus-30 atom here. And this is what we described as an artificial transmutation reaction. Let's look at a brief overview of nuclear reactions. Nuclear reactions are different from chemical reactions. They are even more easier than chemical reactions. On your screen, I have a typical nuclear reaction. There are things you have to know when we are writing nuclear reactions. When we are writing chemical reactions, we don't even need our atomic numbers, because we know that chemical reactions involve electron transfer or sharing of electrons. So we are forming bonds and breaking bonds. When you come to nuclear reactions, they are different. We have to indicate both the mass number of the atom and the atomic number. So in every nuclear reaction, you will see that we will write the mass number and the atomic number. And in balancing them, we have to make sure whatever is on your left hand side is equal to what you have on your right hand side. So if this means that what I have as my superscript, which is the mass number on my left, should be equal to the values that I have on my right, found in the superscript. So sum of all numbers, or of all the mass numbers on my left, should be equal to the sum of all the mass numbers on my right. So if you look at this element on your screen, the mass number is 226 on your left. When you come to your right, you have two different species there. One has a mass number 222 and one has a mass number of 4. When we add the two, we will get the total, which is 226, and this means that the nuclear reaction is balanced in terms of mass number. Let's compare atomic number. On your left, you see that the atomic number is 88. When you come to your right, you have one species having an atomic number 86 and another species having atomic number 2. The sum of the two, or the total, is 88, meaning that the nuclear reaction is balanced in terms of atomic numbers. So when you are balancing nuclear reactions, you have to check whether the mass numbers are balanced and then the atomic numbers are also balanced. The last thing we'll talk about today is comparing. We are going to compare nuclear reactions and chemical reactions. You have to note the differences between chemical reactions and nuclear reactions. It is a likely examination question. Let's compare the two. In a chemical reaction, like I said before, atoms are rearranged. We are just breaking and forming chemical bonds. In nuclear reactions, it doesn't happen that way. We are rather going to change element to another element. So in nuclear reactions, elements or isotopes are converted from one point, or we are converting elements from one form to another different element. In chemical reactions, it only involves electrons. In nuclear reactions, it involves all the elementary particles, protons, neutrons, electrons, and other particles. Chemical reactions are accompanied by absorption or release of small amounts of energy. On the other hand, nuclear reactions are accompanied by large amounts of energy, absorption or release. Chemical reactions are also affected by factors such as temperature, pressure, concentration, and catalysts. And these factors determine the rate or the speed of the reaction. Nuclear reactions are generally or normally not affected by these factors such as temperature, pressure, and catalyst. We would like to end our lesson here for today. What have we learned today? We have been able to describe what radioactivity is. We found that who discovered radioactivity, Henry Becquerel, later worked on by other scientists who are Marie Curie and Pierre Curie. We also described the types of radioactivity to be natural and artificial. We saw what a transmutation reaction is when we convert one chemical element into another chemical element. We saw that transmutation reactions can be achieved in two ways: through artificial means or natural means. Artificial, we are forcing it. We are going to bombard an element with a particle to form a different element. Natural, it occurs on its own without we doing anything. Then we saw how to balance nuclear reactions. We'll solve more problems on balancing nuclear reactions when we meet later in school. So this is the end of our lesson. I hope you enjoyed it. Thank you.